Yes, it's my great pleasure to announce the second part of Professor Ferrari's talk on slot decomposition of the box and ball system. So please, Professor Ferrari, go ahead.
Okay. Good morning. So today we are going to talk about statistical mechanics of excursions and tree decomposition. So there will be no dynamics. The only moment I will mention the dynamics is to say that the properties of the distribution of the excursions that I'm going to describe here imply that the measures that you can construct from those excursions are the configuration measures that you are constructing are invariant for the BBS dynamics. Okay, so this will be two parts, in fact. One will be the statistical mechanics of excursions, where I am going to construct two families of measures and show that they are equivalent. One family is based on is soliton based, so the weights are given on the solitons, and the other family is based on the slot decomposition of an excursion that I will call a slot diagram. And this is like a Young diagram with contents. The box have contents, and the contents have some distribution that I'm going to describe later. So both works are based on joint work with Davide Gabrielli, papers that I am quoting at the end. The first paper is this about the statistical mechanics of excursions. So we start with the family of finite excursion between records 0 and 1. Okay, so I will consider just record 0 is here, and then I have some excursion that can be like that, and then I have record 1 here. Okay, these are not strict excursions. I can touch 0 again at some point, but the excursion is realized when you go down 0, starting from 0. So my space will be excursion of this kind. Okay, could be one of possible excursion is the empty excursion. So when you have a record after the next record. Okay, so in the last talk, on Monday, I talked about this slot decomposition of an excursion that I am calling it a slot diagram. I described how to first you take the excursion that this is the record, so the excursion starts with this colored part and up to here, and this is record 1, this is record 0. Then you perform the Takahashi Satsuma soliton identification, and I identified here with different colors the different solitons. We have here 2, 4 solitons, 2 solitons, 1, 3 soliton, and 2, 1 solitons. And then from the solitons, we have a slot, the slots. So the end of the solitons are correspond to the different slots for the smaller solitons. I cannot go again to the construction, but now we have that the record 0 is a k slot for each k size soliton, and then I have here the 1 solitons are indicated in the bottom line, then the 2 slots. These are the 1 slots, then the 2 slots, etc. And with this decomposition, I get this slot diagram that tells me that there are 2 4 solitons attached to 4 slot number 0, that is record 0. Then there is 1 3 soliton attached to slot 1, 3 slot 1, that is this one. This is 3 slot, sorry, here. 3 slot 1, this is a 3 soliton, and then we have 2 solitons attached to two slots 1 and 4, these two. And then we have two 1 solitons that are attached at one slot 17 and 19. Okay. And then I have this. Yes, is there a question? No. Okay, so now I will define a measure. So for each excursion epsilon, I define the number of k solitons in epsilon as nk of epsilon. And consider a family indexed by soliton sizes alpha k of numbers between 0 and 1, including 1, but including 0, but excluding 1. And I take an excursion and take the soliton of the excursion, make the product of alpha k to the number of k solitons of the excursion, and then sum over all possible excursions and call this will be the partition function z alpha. And we consider the set of vectors alpha such that the partition functions are finite, and then define a measure nu alpha on the set of excursion as the weight of the excursion will be the product of alpha k to the number of k solitons of the excursion and divided by the normalization, that is z alpha. With the convention 0 to the 0 is 1. Okay. So for instance, in here, the weight of this excursion will be alpha 4 to the 2, alpha 2 to the times alpha 2 to the 2, times alpha 3 to the 1, times alpha 1 to 2. Okay? This will be the weight of this excursion, and the normalization factor is written there, is z alpha. Okay, then I will consider the mean number of solitons, of k solitons per excursion. We'll call it rho k of alpha, will depend on alpha, will be just the probability of having nk, will be the number of the mean number is nk of epsilon times nu alpha. And then the size of the excursion will be the sum of the size of the soliton. So the mean size will, and each soliton occupies a k soliton occupies 2k boxes, so k balls and k empty sites. So the mean excursion size is the sum over k of 2k rho k of alpha, and I will consider those alpha given rise to a finite mean excursion size for the measure nu alpha. Is any question about this measure? And next, I will define another measure that I consider now sk of epsilon as the number of k slots in epsilon plus 1. So I consider the slots that belong to some soliton plus 1 for record 0, and consider a family Q of parameters also in 0, 1, including 0, excluding 1. And I call Q the set of vectors such that the sum of qk, these vectors are labeled by the soliton size k. So I ask that the sum is finite, so it's a summable family. And I consider Q plus that the mean size is finite, so it's sum of k qk. And then for Q belonging to Q, I define this measure phi Q of epsilon will be qk to the number of solitons, of k solitons in epsilon, times 1 minus qk, the number of k slots the first question here is to see if this is a probability, and this is what I claim here in this lemma 1, that if Q belongs to Q, then phi Q is a probability measure on the set of exclusions. And the way that you do that is constructing probabilistically a sample of this measure. So, okay, so the first thing is to find the size of the maxima soliton. I am working here in the slot diagram now. So the first thing, I have this QK attached to each one of these lines, okay? And I want to find the maximum size of the soliton. And the maximum size of the soliton, I need to have 4, I need to have that this is bigger than 0, so that the K position is bigger than 0, and that the remaining things are all 0, okay? And then the maximum M will be Qm times the product of L bigger than N of 1 minus QQ. This will be the law of the maximum K such that 0K is bigger than 0. Okay, I am constructing this diagram. See, yeah. In the notation of the previous talk, this with C0. So I fixed the biggest soliton size, and then I have to decide how many solitons put in there, and I will put them. I know that there is at least one soliton there because of this Qn, but I need to know how much are there. So this will be a geometric conditioned to be bigger or equal than 1. And then once that I know the biggest soliton size, I know that in the next step I have how many solitons are. For instance, I have that M is equal to 4 in that. Suppose that I have M equal to 4 and Z 0, 4 bigger than 0. And then I know that, in fact, with that probability, I have Z04 equal to 2. And then I know that S3 will be equal to 1 record plus 2 slot for each 4 solitons. So there will be 5. Okay. S3 will be 5, and then I put a vector will be Z. This vector will have 0, will be the vector until Z4, sorry, 3. Okay. And I put them with geometric identically distributed with parameter QK. Okay. And then I know in how many solitons I have in the excursion. I can again construct S2 that will be a function of the number of slots, 3 slots and 4 slots, etc. up, and then put geometrics with parameter Q2 up to S1. Then I put S1 and put the last vector. Is this construction clear? Okay. So the resulting diagram has a low PQ because, in fact, the measure phi q of the maximum is given by this expression. I need to have at least one k-soliton with probability Qm, and then I have to have no k-solitons for L bigger than M. And then, given that I know how many solitons I have in the 0 m slot, I put a geometric conditional to be 1 at least with parameter qm, and then this gives me how many. If I know all the future, all the things that are up above k, I can construct k because I know the number of solitons that depend on the things that are bigger than k. So y is a vector that will have k coordinates determined by zeta k plus 1 infinity for the other coordinates, and nk will be the sum of the coordinates of y. Okay, it's like put n independent geometrics with parameter. Put sk independent geometrics with parameter qk. Okay, so the main result here is that these two measures are equivalent. So if we have alpha in A, so that the measure nu alpha exists, and Q is defined recurrently in this way. This is a complicated construction, but Q1 is equal to alpha 1, and then recurrently you define Qk as alpha k divided by the product from 1 to k of 1 minus Qk times 2k minus j. This is a number of j solitons in number of j solitons produced by k. And then if you have Q in Q and define alpha equal AQ in this way, alpha Q k equal to Qk times the product from 1 to k minus 1 of 1 minus Qk to the k minus 1. Then these two maps, Q and A, are bijections, and one is the inverse of the other. And most important, the measure nu alpha is equal to the measure phi q. So starting from a construction from the distribution nu alpha, that is a distribution based on solitons, that is what you find essentially when you have a measure on the ball configuration. You can pass using this operation to a configuration based in the slot diagram that is that then will give you an infinite volume measure in the whole set of vectors given by the components of the configuration. Okay, the proof of this, we discovered that taking nu alpha and computing the partition function and finally arriving to this formula. But here, this I am not going to show you that, a bit involved. But I can show, once that you know the formula, you can show that if Q is equal to Q alpha, then alpha belongs to, if Q belongs to Q, that if Q belongs to Q, then alpha belongs to A, and nu alpha is equal to phi Q. So I am starting from this expression for phi q of epsilon, and then you use the definition of this is because of the definition just of phi q. Then you use the definition of sk, that is the number of k slots in the excursion given by 2 times j minus k the number of j solitons for j bigger than k, plus 1 for the record. And then here you have rearranged the sums. So here the sum was going from k to j. So you invert the sum and the product here. And then you get this expression. And this expression is already in the form alpha k to the k. So alpha will be exactly that. Okay. This is just a rearrangement from here to here. And but with this formula, you already get that the z alpha must be this product here, because this product, you know, that is finite because q belongs to q. That is the sum of this thing is summable, and then this gives you nu alpha. Okay, so this is important because in fact we started to use a random walk excursion, but a random walk excursion you take that the balls are distributed according to the product measured with density lambda that is less than 1/2, and the excursion of the random walk will have the probability soliton based measure nu alpha, because for each soliton you have to go k, for each k soliton you have to do k steps up and k steps down. So you pay, for each soliton you pay lambda times 1 minus lambda to the k, and then you have to pay 1 minus alpha minus lambda to go down. So you will have lambda to the n to the size of the excursion, no? To the sum of n k of the excursion, but also 1 minus lambda. And then at the end you have to do 1 minus lambda to go down, okay, for the excursion, for the record. And so this gives you z alpha is 1 minus lambda to the -1 because it's multiplying here. And then you can compute the mean excursion size because you have that the records are, the density of records is 1 minus 2 lambda, because lambda is the density of particles that are of particles, and lambda is also the density of boxes that are not records. So the records is this difference, and you can compute the mean excursion size is the mean inter-record distance that will be then this one. The parameters, in this case, the parameters Q alpha can be computed recursively, explicitly. You can take a lambda and compute them using the formula that I explained before, but we didn't find any expression, any explicit expression for them in this case. Okay, now I know the distribution of the slot distribution of say the excursion of the random walk, and I want to take conclusions about the whole configuration of the random walk. So I start with a family of excursions, epsilon I in Z, and construct a walk C that will depend on the excursions as follows. So you put a record at the origin, and then put the remaining records separated by the excursion size. So you look at the excursion size 0, and then you put a record after it, the record 1, and then the excursion size of 2, and put a record there, and so on. And then in the middle of the two records, you insert or attach the excursion like that. So it's something like that. So you you have a family of excursions. So you have, for instance, here an excursion 0. Then you have this excursion 1. And then you have another 0 here, another 0. You have 2 0 here. Then you have this excursion 3, 4. And then 3 empty excursion, and you have this other excursion here, 5. Okay. Okay, so then you perform the soliton identification and get all these solitons here. And then for each one of these soliton, for each one of these excursions, you construct the slot diagram, that is this one. Okay. So for this excursion 0, that is the corresponding to record 0, has a slot diagram Z0, Z1, etc. Okay. And then you have here, I copied the previous picture. And then what you do is just the slot like that to construct a diagram like that, a double infinite diagram like that. In the other side, you'll do the same in the other direction. Okay. And then you get this double infinite function from Z plus times Z. Okay. Is any question about? Okay, so the proposition is the following: that if you have independent excursions with distribution nu alpha, then you will have in this diagram here will have independent lines, and that is this. And each line will consist of independent geometrics. This diagram is what I call the juxtaposition of the small slot diagrams. Okay, so this has important consequences for BBS, because it tells you that any measure that is invariant, any measure that is of this form of measure nu alpha, including random walk and also Markov chain, you can do as an exercise to show that Markov chain can be expressed in terms of soliton weights. And then if you take the slot decomposition of random configuration eta distributed according to a stationary Markov chain in 0, 1, so you have zeros and ones, but the jump from 0 to 1 depends on 0 and 1, so like the Ising model or just a Markov chain. And you ask that has an invariant measure nu, and this invariant measure nu has weight less than 1/2, because we need that the density of particles be smaller than 1/2 in order to construct the process and to find invariant measures. And then it will satisfy these two properties according to the previous proposition. So each one of the lines will be independent, and each one of the lines will consist of independent, identically distributed geometrics, random variables with parameter 1 minus qk. Qk is related to alpha with this formula here. Unfortunately, I cannot derive from here. I can only do Control Z. Okay. Well, but in the theorem that with Nguyen, Rolla, and Wang that I described in the previous talk, I showed that, that if you have a ball configuration whose components are independent and satisfy some conditions that are satisfied here, then the distribution of the configuration is invariant for the dynamic. The measure of the configuration is invariant for the dynamics. In particular, as a corollary, I will have that a stationary Markov chain in 0, 1 with invariant measure nu and nu less than 1/2 is invariant for the BBS, and this included, of course, the IID Bernoulli random variables with parameter lambda less than 1/2. I just mentioned that this was already known since a long time ago for the IID random variables, but also for more recently, Croydon and Sasada proved that, and Sugimoto, I think, proved that using reversibility, these two properties. The point here in that construction is that the set of measures mu alpha is much bigger than the Markov chain and Bernoulli cases, because you, for instance, you can erase all solitons of a given size k, and you get a measure that with long range correlations and longer range correlations is still invariant for the BBS. Okay, this is what I wanted to say about the statistical mechanics of excursion and its conclusions. So, and the identification of the measures and its conclusions, corollary for the set of invariant measures for the BBS. Before passing to the other topic that I wanted to describe briefly, I would like to know if there is any question about this one.
Yeah, just in physics, I think there is something called Boltzmann weights exponential beta k times the energy. And I think it should be the same as your first measure, but I would like to know if you agree with that. There is some construction, for example, Kuniba, he looks at something called thermodynamic beta, and that's...
I suspect that they are pretty similar, but I am not... I'm not very familiar with it. This is, you are talking about this rigged configuration, rigged...
sorry, I did not hear you.
No, I couldn't understand well the work of Niva, so I will be happy to know if it is the case.
Well, I could discuss that by Zoom or by some other way. Okay.
Okay. Yes. Yes. I suspect that there is something, because I saw something that looks similar, but I'm not sure.
Okay, we can discuss, because I think it should be the same, but I think okay.
Okay. Who was talking?
My name is Vincent Pasquier. I am a collaborator of Atsuo Kuniba.
Okay. Thank you. Okay, so now I am talking about something more. There is no measure here. It's just at the end I will have only a small corollary for the description of trees related to that. So this section is based on a work on the other paper with Davide Gabrielli. So I will propose an alternative decomposition of an excursion using a bijection between excursions and planar trees. And this will be a variant of the classical bijection of a strict excursion when you don't allow a touch zero. There are things that are a lot of works, Cyril Legal, Evans, Aldos, etc. I am not pretend to be complete here. So this tree representation of excursions is classical thing. So you have this excursion here, epsilon, and then you divide it in regions with horizontal lines that are at height, integer heights, like that. And then at each connected component, you associate a node. Okay, you put a node here, a node here, etc. Okay? And then you put also a node for the record, but it's outside, it's below all of them. And then you draw an edge between the nodes sharing a boundary. Then you will have so this node is connected to this to this, etc. Okay, and you get this picture down there. Yeah, and the root is associated to a record. Okay, now this is a planar tree, right? What you get is a planar tree. So this planar tree, I am copied it here, and I will give an identification of branch. Okay, so the first branch identification is the following. You put at each leaf a different color, like that, and then go to the next generation to be updated. The next generation must have all the offsprings already colored. Okay, so the next generation from here are these nodes here. Okay. Okay, then you put the color of the node of the branch of the biggest branch on your right. From the biggest branch, starting from that node, in the direction opposite to the root, you choose the biggest one and take the color of that one. For instance, here there is no problem that there is only one branch, so this node takes the color of it, that is red, this is green, red, blue. Okay, so this blue should be different of this, and this red different from this, because I said the different colors. No, but since I know the end of this, I put the same color. Okay, but here is the difference. I have two colors here, but I take the color of the right one. Okay, then I have these three. In the next generation, I have these three nodes that to update. I cannot update this one because these are not already not colored yet. And then I do the same thing. So this take color green, blue, because the biggest. There are two biggest branches, and the biggest one, the right one, is blue. So I take color blue, and this already the biggest branch is only one, so I take the same that color, that is one. And then for these two, I just take the biggest branch, that is there is this and this are the biggest branches, and I take the right one, so it's blue again. And this is blue again. So I get these configurations of colors. Okay? Then I call a K branch is a one-dimensional path with K nodes, all the same color, and K edges. One of them is incident on a node of different color. So here, this picture is the same of the previous transparency. So we have identified 2 4 branches, 1 3 branch, and two branches and 2. Okay, then there is another branch identification that I will jump, and then there is a third branch identification that is the following. This works more like in the identification of solitons. So you orient the tree towards the root, just to construct the algorithm. And then you remove the root. You remove the root, and then you see if the root is not there, you will have two big branches arriving there. You take the rightmost biggest branches. There are 4 branches that are these ones, and then if there are 2 passing from the same node, you take always the rightmost one. Okay. Then you erase those 2 branches, and then you take the longest branch, that is this, and put them green. Erase that, and you identify 2 red, and then erase the 2 red, you identify the 2 violets. Okay. Now you take these branch identification give you the same tree. When you put back the the things into the tree, you get the same tree. Okay. Now you put back the branches into the excursion and color. So each branch corresponds to a region that is bounded to the left and right by parts of the path. So you color that part of the path with the same color of the branch, and then you will get a soliton identification that I will call soliton star. You can see that in this soliton identification, there are no solitons that are going downwards. All the solitons are going upward. Now we will construct the slot diagram from the planar tree. So we use the branch decomposition tree to identify K slots. For instance, I know, so the 0 will be a 0 slot for any size. In particular, I know that I have a 4 size, so I will identify the 0 as 0 slot. I have this part here. It's dividing is cutting the communication between these two parts. So it's like a semicircle here. Okay. So I put the 4 slot. Then in the 4 slot, I attach 2 4 branches, and I see where are the places where I can attach 3 branches without breaking the rule that these are 4 branches. Okay, and this is very similar to what I did with the solitons last class. So the places where you can put 3 branches are these 4, this 5 here. You can put here. If you put a 3 branch here, you will get a 5 branch, and you don't want that. You want that 3 branches. The biggest are the 4 branches. And then once that you attach 3 soliton, you can decide where you can put 2 branches, and these are the places where you can put 2 branches. And then you attach the 2 solitons, and these are the 21 places where you can attach 1 branches. I will call a K slot star the place of the node where you can put a new K branch without changing the configuration of the already present L branches. Okay? And then you get this slot diagram, and from the slot diagram you can reconstruct the tree going back. How I am doing with the time? Do I have a?
You have about 4 minutes, well, 3 or 4 minutes left.
Okay. That's why okay, so now if you start with this, if you start with the slot diagram of the excursion induced by the tree diagram that I constructed with this branch, you get these configurations of the slots that are slightly different than the configurations of the lot of Takahashi Satsuma. But here I put a picture with, in the upper part, you have this slot decomposition coming from the tree decomposition, where the solitons are going up, but you see that the position of the slots, the position of the solitons look different, and the position of the slots look, some of them coincide, but others look different. But if you do the slot diagram, they coincide. You have exactly the same slot diagram for both for both representation of the slots. Okay, as a nice corollary is that this is a contribution to another area, that is this area of branches of trees associated to excursions. So you can describe the branch distribution of the excursion of a tree using the equivalence between the measures nu alpha and phi q, and you can start constructing the slot diagram, and from the slot diagram construct the excursion of the tree. So I think I finished here now. Thank you.
Thank you very much. Are there any questions, not only regarding the second part, but also the first part? If not from the room, are there any questions from the online participants regarding the talk? There is one in the room.
So thank you very much. Makiko is talking. So I think the question from Professor Pasquier is related to the generalized Gibbs ensembles. At least for periodic version, periodic box ball system, we can construct just counting the number of solitons in this period, and then we put parameter beta k for each size k, and we just consider Gibbs measure like exponential of beta k times number of solitons in this period, and we add them and just take this as a weight. And so the question is, can we do this also on the whole space, not periodic space? And so I think what you did is quite close to that. But so do you think it's really the thing, the whole space version of such a measure?
Yeah. You have a whole space measure. I think that this picture was. I'm not sure if I understood well your question, but I think that this picture answered your question or not. You put the excursions with independent.
Yes, maybe yes. So first, if we do not have a finite expectation length of the excursions,
then you can have infinite, because this construction works also for the case lambda equal to 1/2 for a random walk. The problem is that that you have to condition that you have a record at the origin for the symmetric random walk. And then you will have independent excursions with geometric distributions. But but the expected size of the excursions is infinite. So
okay,
but you can still do it. Yes,
needed. And so can we prove that this is the limit of this periodic version? So if we consider just periodic system, and we take so actually I also want to do this, but so far it works only for Bernoulli or Markov case, but we expect this should be the limit of the size, period size n of some.
No, we started thinking about the periodic things, but then realized that in fact it's much more comfortable to work directly with excursions. So to allow the size of the circle or whatever the variable.
Okay, so but maybe we expect.
But I believe that the answer is that probably yes, that you should be able to compute, because in the periodic system you should compute locally, should converge to this kind of things. Yes.
Yeah, that is what we really want to understand rigorously.
Yeah.
Okay. Yeah. Thank you. Yes.
Okay. Thank you.
Yes, just one more question.
Yeah, I think it's related to that. So can you prove that you have clustering for these invariant measures, meaning that at different positions in space, the configurations become independent at large distances?
correlations go to zero at large distances. Do you understand what I mean?
Yes, I guess so. So you want the probability to have a ball at 0 and at x and x
Yeah.
b if they are independent.
Like the density of balls around some point at 0, some point x. That's
just
probably a necessary condition for the limit of periodic to infinite system to exist.
yes, yes, probably. I didn't think about that. I'm not sure,
Okay.
but I think a good question.
Okay. Thanks.
Thank you.
Any other questions? If not, I think we'll thank the speaker again.